Good afternoon, everyone. Thank you for attending this session, HPC Technology. Welcome to the CHPC conference. Today we have two speakers, and both will speak for 30 minutes. We have Dr. van der Westhuizen, who's going to be speaking on configuring the CALD ASR toolkit for the Lengao cluster. And also we got Rudolf Pinner from Boston Children's Hospital, who's going to be telling us stories from the frontliners, telling us the good and the bad and the ugly of building an open source distributed platform for scientific compute, software, hardware, community, and he'll tell us all the rest. When you look at your screens, you will see there is a Q&A chat. Please use that Q&A chat for questions that are directed to our speakers. I will read them at the end of each session, and the speaker that this question is directed to will answer a question. Thank you. Over to you, Dr. van der Westhuizen.
Okay, I'm Untitled Chapter. Thank you for attending my talk. We'll be looking at how we configured the CALD speech recognition toolkit for the Lengao cluster. But first, a quick overview. I'll briefly introduce the DSP group. Then I'll briefly show what the United Nations Global Pulse Initiative is. Then we'll look at what automatic speech recognition, or ASR, is. And I'll show how we configured the CALD ASR toolkit to work on the cluster. And finally, I'll show a practical example of an ASR system, in this case for the Bambara language. So this is a photo of the DSP group in the times before social distancing. We're part of the Department of Electrical and Electronic Engineering, and our lab has capacity for about 25 people working on both software and hardware projects. For interesting areas of research we are working on are speech processing, so that includes ASR, then cough monitoring in TB wards, animal tracking and anti-poaching devices, and assistive technologies for people with disabilities. Our DSP group is involved in a project with the United Nations Pulse Lab in Kampala, Uganda. In this project, we use speech processing systems in a number of African languages for analysis of public discussions on broadcast radio shows. So you might wonder why public radio and not, for example, social media. In rural parts of Africa, internet connectivity is limited, and in comparison, broadcast radio and phone-in talk shows are more ubiquitous platforms for voicing opinions. Topics of interest include, for example, violence against women, disease, famine, and natural disasters. Timely detection of these topics help the UN determine regions where humanitarian relief efforts can be focused. The links on the slide go to websites with more information. And this is a photo of the team working in Kampala with a link to their website. So let's look at automatic speech recognition, or ASR. So as the image shows, it's the conversion of human speech to text using a computer. This is an overview of the speech to text process that happens on the computer. First, we capture speech using a recording device and convert the analog signal to a digital representation. The speech signal then gets coded into an acoustic feature representation. This is typically a frequency domain representation of the short time frames, and it forms a time series. These frames are then input into the ASR decoder that produces text as output. An ASR system consists of three components: the acoustic model, the language model, and the pronunciation dictionary. The acoustic model that models the basic sound building blocks of speech in a specific language. The acoustic model is trained on labeled speech data, meaning we need speech audio with its corresponding text transcriptions. The language model models word sequences of a language, and that is trained on large amounts of text data. The pronunciation dictionary forms a link between the acoustic models and the language model, and it describes how each word in the vocabulary of the language is pronounced. It maps the text representation of a word to a sequence of sound units. The pronunciation dictionaries are typically compiled by linguistic experts. One of the leading toolkits for ASR research is CALDI. It is open source and actively being developed, and it uses state-of-the-art machine learning techniques such as artificial neural networks. CALDI includes many experimental recipes, and each recipe is meant to work for a specific data set or corpus. So if you were to develop your own data set, you can contribute your recipe to the CALDI codebase. CALDI can be set up to run on a single PC or on a cluster, and the default cluster setup is meant to use the SunGrid engine. To configure CALDI for a cluster is well documented, but it is assumed that the user has full control over the cluster. In fact, the documentation describes how to set up your own cluster in order to use CALDI. There are advantages and disadvantages to setting up your own in-house cluster compared to using a large shared cluster, and here I list a few. So if you as a researcher set up your own in-house cluster, you have full control, but it's also up to you to fix problems that you encounter. Your resources are also limited by your own funding, and you are solely responsible for maintenance. That can also be an advantage if you want to perform upgrades to the cluster. On the other hand, on a shared cluster, you may have limited or no control over the cluster, and usage policies and restrictions may apply, but you have on-site and expert support and abundant resources at your disposal, and you're not responsible for the day-to-day maintenance. When the disadvantages of an in-house cluster outweigh the advantages, migrating to a shared cluster becomes attractive. CALDI is under continual development, and to remain up to date with the latest version, one has to update the local source code and recompile the binaries. This can become a hassle for system administrators if CALDI users each require their own specialized version of CALDI. To overcome this, we use a containerization approach. We use the Singularity software to create a container or image that contains a compiled instance of CALDI along with the required third-party libraries and the NVIDIA driver for GPU computations. In this way, the user is responsible to maintain the version of CALDI they choose to use, and this is shown in the bottom right block. The experimental recipes live outside the container in this inner block on the left, and the execution of specific parts of the experimental recipe is controlled by a wrapper script that makes calls to the experimental steps using the Singularity image. Yet another wrapper script at the outer layer handles the submission of either CPU or GPU based jobs to the cluster. So let's look at the outer layer script that handles the job submissions. An experiment will start when the user executes the submission script. This submits two sequential jobs, one on a CPU queue and the other on a GPU queue. The CPU-based job is executed on one node where all 24 cores are used. Upon successful completion, the GPU job starts. This is a small job that should take less than an hour of wall time and is only used to calculate the duration of one GPU training iteration. Once we have an estimate for one iteration, we can estimate the total required wall time for the total number of GPU iterations. If the estimated total wall time exceeds the maximum wall time for a job, the GPU training is divided into smaller jobs that observe the maximum wall time limit. These jobs are then automatically submitted to the GPU queue. This is followed by the final CPU-based job, which is the system evaluation step. Any of the GPU queues can be used as long as the choice of queue remains consistent throughout the whole experiment. The resources that we request per GPU queue are shown in the table. The time to run an experiment can vary greatly and depends on the size of the training dataset and the architecture of the neural network. The experiment I'll discuss next takes about 24 to 48 hours to run. Some of our larger experiments take approximately 450 hours to run. Since we are using Kaldi in a single node mode of operation, we are limited by the number of cores of a node. So this means 24 cores for CPU-based jobs, and the table on the previous slide showed the values for the GPU queues. Experiments can be scaled up quite easily. Since experiments can run fully independent of each other, many experiments can be run in an embarrassingly parallel fashion. Kaldi doesn't make use of inter-process communication or message passing. Let's look at the usage example for the Bambara speech recognition system. The Bambara language is spoken in Mali by approximately 80% of the population. There are about 1.1 million first language speakers and 10 million second language speakers. No commercial speech or text resources existed for ASR development, and these had to be developed from scratch. This was done by the team in Kampala. The datasets used for ASR development look as follows. The speech dataset used for acoustic modeling was developed in-house from public broadcast radio recordings. These were manually segmented and then transcribed by first language speakers. So the in-domain monolingual Bambara training dataset comprises approximately 10 hours of speech. We augment this with two Ugandan languages, Luganda and Acholi, comprising approximately 19 hours of speech. The development and test sets each include 45 minutes of Bambara speech. The Bambara text used for language modeling is taken from the transcriptions of the radio speech data. That's approximately 180,000 word tokens. Additional text collected from the internet makes up approximately 570,000 word tokens. The pronunciation dictionary uses a letter-to-sound mapping approach, and this is a fair assumption since there is a high correspondence between how words are written and how they are pronounced in Bambara. I just quickly want to show an example of what the transcription process looks like. We used the Praat annotation tool to do the transcriptions, and from this screenshot you can see in the top section the waveform of the speech signal displayed. In the middle section there is an image of the spectrogram of the speech signal, and in the bottom section the text transcriptions are entered. So as you can imagine, this can be quite a time-consuming process, doing it all by hand. For the development of the ASR system, we of course use the Kaldi ASR toolkit. The acoustic models are trained using a multilingual training approach. This means that we pool the Bambara acoustic training data with the training data of the two Ugandan languages. The architecture of the models look as follows. The input feature layer is followed by a number of convolutional layers that are followed by time delay layers with factorization. A spectrogram augmentation layer is also included, as this was found to further improve the ASR performance. This diagram shows a simplified structure of the multilingual neural network acoustic model. At the bottom of the diagram, the input layer to the network is presented in turn with acoustic feature frames from the set of training languages. The hidden layers of the network are shared by the languages. The language-dependent output layers enable language discriminative training of the shared network. However, the expectation is that the earlier layers of the network will learn aspects of human speech that are common between the languages. Like I mentioned earlier, the pronunciation dictionary uses a letter-to-sound mapping approach. The vocabulary size of the pronunciation dictionary is just over 16,000 words. Okay, let's look at language modeling. The language model models the probability of a sequence of words, and it is trained on text data. For the Bambara, we use a trigram language model that was trained on the radio transcriptions and the collection of internet text. The perplexity of a language model is a measure of the confusability that exists in the model. In other words, the lower the perplexity value, the more certainty the model has. The perplexity of our trigram model is 188. The perplexity value can also be interpreted as an average branching factor. So when the model has to determine a likely following word given a history of words, it has an average, on average, a choice of approximately 188 words. The perplexity value can vary according to many factors, such as the language model order, the language itself, the writing system used by the language morphology, and the test data that the perplexity was calculated from. Just as a comparison, an often cited perplexity value for English is approximately 250. So finally, how does this ASR system perform? This table shows word error rate results for the Bambara test set. This means that lower values are better. We trained 5 different systems using different neural network architectures and different configurations of training data. The dataset B8 is a slightly smaller dataset of Bambara speech, around 8 hours, while dataset B10 is the full 10 hours. If we compare systems 1 and 2, we can see that they differ in the type of neural network architecture. System 2 has the additional convolutional neural network layers, which result in an increase in system performance. If we compare systems 2 and 3, we see the difference is in the configuration of the training data. System 2 was trained on Bambara, Luganda, Acholi, and some additional speech data from other languages. System 3 was trained on a more carefully selected set of languages, that is only Bambara, Luganda, and Acholi. We see that System 3 outperforms System 2, so we can conclude that the omission of certain training data sets can improve system performance. A reason may be that these other languages or training data sets are not as representative of the Bambara target domain. If we compare systems 3 and 4, we can see the addition of some more Bambara data as well as the spec augment layer that was added to the architecture. These additions result in a further decrease in the word error rates. Optimizing a speech recognition system can be an arduous task. As shown here, it includes many experimental runs to investigate different model architectures, training set configurations, and hyperparameter tuning. In this respect, a large cluster is an invaluable resource that enables us to do these tasks in parallel. In conclusion, let me summarize what we covered during the talk. I introduced the DSP group from Stellenbosch and mentioned some of the research projects that we are currently working on. I then introduced the United Nations Global Pulse Initiative and the radio content analysis project we at the DSP lab are assisting the UN with. Then we covered the basics of automatic speech recognition and what such a system entails. We then looked at the Caldi speech recognition toolkit and how we configured it to run on the Lengao cluster while taking the queuing policies into account. And finally, I showed a practical usage example of speech recognition using the Bambara language. Here we saw that the use of a cluster enabled us to run many experiments in parallel, which helped to speed up the optimization of the speech recognition system. I thank you for your attention, and any questions are welcome.
I don't see any questions in the Q&A session. I believe people do not have questions. I'll wait 2 more minutes just to wait for questions. If there are no questions, Prof. Rudolph can start with his presentation. Hello again, everyone. Um, Prof. Rudolph Benar is ready for his talk, where he's going to be telling us about the good, the bad, and the ugly, building an open source distributed platform for scientific compute, telling us the side, all of this on the side of software, hardware, and the community. Over to you, Prof. Rudolph, when you're ready.
Great, thank you very much. Can you hear me? Should we first check that that's working?
Yeah, we can hear you.
Perfect, all right. So hello, everyone. My name is Rudolph Pinar. I'd like to thank the organizers for the opportunity to speak here today. I actually happen to be in Cape Town for the next 2 weeks, and it's wonderful to be here. And I hope for the audience that there's at least something interesting in this talk. I'm probably going to say there's going to be nothing profound in it, but maybe hearing some stories of our experiences might be of interest, might percolate some connections. Let's hope that that's what happens. All right, so a copy of this talk is also available on our lab website, the link below, which is very long, but if anyone needs it, I can happily supply that again. And there's also a video available, which I uploaded earlier. So a little bit about me. So I'm a staff scientist over at Boston Children's Hospital in Boston. I'm also an assistant professor in radiology at Harvard Medical School. At our lab in Boston Children's, I'm the technical director of the Fetal Neonatal Neuroimaging Development Science Center. It's quite a mouthful, but it's that little thing over there. Where I'm basically in charge of handling all of our computing environment, cloud interactions, and we also develop kind of scientific compute solutions, and as well lately been working very hard on this kind of open science, open source platform, which is what I'm going to talk about our experiences today. And there's a little picture of me in the before COVID times when people would still get together outside and do things like go for a run or whatever. Let's hope we get back to those times soon enough. Anyway, in this talk, I'm going to briefly touch upon some of our experiences and the choices we've made in developing this kind of open source containerized compute platform that we call CHPC. I'll talk about the choice of our development language, the underlying technologies we decided to use, the deployment platforms, documentation, very much so, DevOps and continuous integration, and very importantly, community. How do you seed community and how do you grow community? And again, I don't have any silver bullets, magical answers for any of these things, but I'm happy to talk about our experiences on these. So it'll be a quick sort of over the top, on the surface kind of overview, because we can't go into too much detail, but we can always come back to further discussions. So I'm talking about this thing called CHPC. Maybe I should just pause a bit and say, what is this thing called CHPC? It's kind of a platform as a service that we developed in-house initially at Boston Children's. And then as time went on, we began collaborating very deeply with Red Hat of Red Hat Linux out of their Boston offices. They have this innovation lab. And we've developed this thing called CHPC, which is a completely open source. It's available on GitHub and Docker Hub. It's fully containerized. And what's unique about CHPC versus other similar things, which I'll briefly touch on, is that we can link together chains of containerized computations, which doesn't really happen much. We're also on premise. Our solution can run completely on your laptop if you felt like it, provided you have a really reasonably decent laptop. Your laptop, your workstation on HPC, also on the cloud, and you can actually have different parts of your workflow chain run on different compute environments. You could have sensitive information in your local network that you don't want to leak out, so you run that computation on your laptop for argument's sake, but other parts of it you dish out to the cloud to crunch on better hardware. So over here, just as a quick, again, giving some kind of groundwork. So we're sort of in this silo over here on this third one, platform as a service, where we take care of everything on the orange. Really, that's what CHPC takes care of. And a developer only worries about their applications and their data. This is quite different to normal kind of research computing world, where researchers who then act like programmers live very much on the far left. And they are responsible for everything: their data, applications, the operating system, versions of libraries of programs. And they spend a lot of time doing stuff that they don't really like to do, right? Which is managing the infrastructure around their compute. So one of the things we try to do with Chris, at least from this perspective, is to leverage all the platform benefits to users and take care of that complexity for them for a very small price in our mind of wrapping your compute in a particular kind of Python wrapper. And then you get the benefit of this distribution and the platform. So Chris was basically created to address the basic need of running some type of analysis on any kind of unstructured data, pretty much anywhere. Anywhere is sort of within quotes, it should be, because it depends where you've installed the system. But the platform makes no presumptions upon what the data looks like. It also makes no presumptions really about what the compute on that data is, as long as it can be containerized. And we have like we think a modernish web-based interface. Our entire backend is completely separate from our front end, which means we actually can have multiple user interfaces. If you have a particular workflow, let's say you're doing some kind of MRI analysis and you just want a clinician or a doctor to hit upload data and start, well, we can build those kind of very focused web interfaces for you where they don't have to really deal with any of the intricacies behind the scenes. But a picture is worth more than 1,000 words. Let me give you a quick overview. Here's a live version of Chris that's running. I'm just going to go to a different tab where it's a little bit bigger, just to give you a very, very quick overview. And I'm not going to talk about it in too much detail because that's not the point of this talk here. But once you've logged into the system, and here I hope this is all very visible. Let me make this a bit bigger. You have this kind of tree structure on the left, which I'm sort of circling. An upside down tree, because the root of the tree is way up here. And this is actually some computation that is currently still running. But everything starts with a root. And this is some kind of data set that you have seeded the system with. And all of these other branches and other nodes are computations that have grown out of that one particular data point. For argument's sake, I can click on this node here, which hasn't computed yet. I can add another node to it. Here's my list of compute. These are all containerized computations. I can click through. Again, I'm going to go to this very, very quickly, but I can choose some parameters for this, et cetera, whatever these might be. And as I click through, then it adds this node to my tree and it schedules the compute ready for it to happen. This currently is all happening on my laptop. But of course, all of these particular nodes can exist anywhere, including the cloud, which is what we usually target. Now, each of these nodes is a containerized computation with all of its own internal data. For argument's sake, if I click on this first one over here, the root, I have a file browser, if you will, but this is now all web-based. And here I have the data that I have seeded this particular computation with, and this is an MRI data set. So I'm going to quickly open this in the viewer. We can have a quick look, at least it loads relatively quickly. The joys of doing things locally. And so here I can interrogate my initial data set, provided it's something that I can visualize. In this particular case, I can. And here I can visualize my MRI data and just quickly go through it, make sure, hey, this is in fact what I wanted to analyze or do some computations on. And then I can build a kind of processing tree built off that. Right, so the point of this, again, is not to get too involved in how Chris works, but more how did we build community and stuff around it. So I'm going to just peel away that shiny front end and just give a quick sketch of some of the innards of Chris to my point of how do we try and manage and build these systems. At the heart of Chris is a thing which we call Cube, which is the core component that contains data, all the data you've processed, all the users, all of the representations of the plugins that the system can run. And it's very much the core of the system. And let's just throw a network boundary over there. And let's assume you are living over here on that side of the network boundary. And you communicate with Chris. And all of these things I'm going to quickly sketch in right now. All of these squares are completely self-contained, really, in their own right, containerized compute services. So we can connect to the system using a REST API. And I'm just going to add on some more blobs over here. Here we see there's something called a PFCon, which is a coordinate here. Here we have the official CHRIS UI, which is what I just showed you very, very briefly. And we can continue adding more parts to the system. Let's assume this part of CHRIS lives inside its own network, say at a hospital or at a university or even in an office or a corporation, whatever the case may be. But far away is and let's wire them up, but far away on the other side of the network lives other services that are part of the ecosystem. These handle IO and process management. And in fact, these ones over here will handle the processes as they might run on a cloud backend service. There's also a CHRIS store, which is sort of like the Apple store or the Google store, at least generally analogous to that. And then of course we have GitHub and Docker Hub as our source code repo and our container imaging repo. Again, the point of this is not to get stuck in the detail. We can wire them all up together, but more to show the components of this system. Right, so what are some of the factors that govern the creation of a new platform? I'm not sure what happened with that question mark over there. Let's just ignore it. Why do we create something new when other things might be good enough? Well, we can create something new to scratch a particular itch. That's usually what happens, right? There's something very specific we want solved and we know how to do it. We can have a very high problem specificity in it and tailor our solution to scratch our itch. And we can ramp up very quickly oftentimes, but it's a deceptive ramp up. Oftentimes you can get to 80% of your needs with 20% of the effort. The remaining 20%, of course, takes 80% more work. And it's that remaining 20% that oftentimes contains very useful features. Of course, creating something new is exciting, right? An existing solution doesn't always fit, but it can definitely save up the ramp up time. And if it's of a high quality solution, it's definitely worth investigating. It's very good for small teams or solo developers. Of course, CHRIS isn't the only game in town. I'm not going to talk about all of the other things that are similar to it, but there are a lot of services in the kind of open science compute environment that offer the same conceptual thing, right? Where you upload data, you run some kind of analysis on it, and you get results. They all differ in their details, very significantly so. So one thing that is very important that we like to think about is this development lag time. Many projects, particularly open source projects, are snapshots into some reality that they chose when they began developing the system. And the larger and more established a project, oftentimes the longer the lag time or the lead time to get something out the door. And by the time it arrives, oftentimes the older the technology is. New tech is often added as a retrofit or an afterthought. And if we go back over here to this quick table, CHRIS is the only system to our knowledge at this point that uses containerization to the extent that it does. Most of these other solutions were developed in the time before containers really were such an interesting and good thing. And they either have containers retrofitted awkwardly or they don't have them at all. So of course, we have the other problem in open source communities, especially if you have a liberal kind of MIT type license, that things can very easily, like rabbits, open source begets open source. New things can split off very, very easily. It's always tempting to keep in mind before you fork something to see if an existing thing works. You know, what's a perfect example of this? Well, here's a quick chart of probably the most famous open source project, the Linux distribution or Linux kernels. And here we just have a quick taxonomy over time of how many distributions exist. And I think at last count, there were 1,000 plus, right? A lot of them are derivations of a couple of core distributions, Debian, Slackware, Red Hat over here. And even at the bottom, we have Android as a sort of bona fide Linux distribution. Okay, so let's get into the meat of some of the stuff that we've been experiencing. What is the core language we chose? Well, we chose Python. And the good of Python is it's extremely well established. It's full featured. There are frameworks for Python that can be very good. And it's certainly the language that is used for science, AI, and machine learning type applications. The bad of Python is we've experienced considerable, what I call universe creep. And that is the space of Python libraries is so large and you end up using so many external libraries, they begin to creep with time. Updates occur, they might break your code. It's very hard to keep track of these things. And as we chose Python as our core language, even though the CHRIS system was designed to work with almost any kind of plugin that one develops, we found that we began to lag support of other languages. Like it's more work to get a C program in CHRIS than it is to get a Python program, for argument's sake. And the ugly, well, I'm going to say frameworks, which are very much a good thing, can also be an ugly thing, partially because of their complexity. Django is a very hard framework to get into. You need a lot of investment beforehand to get into it, which leads to a struggle for new developers oftentimes. The core technology that we've based our infrastructure on, and which I've alluded to explicitly, is Docker. Now, Docker and containers are, as we probably all agree, are very good for a couple of things. They're very cross-platform, and particularly in scientific compute, they're repeatable and reliable. If you run the same container, you'll get the same results no matter what operating system you're running your compute on. And this is extremely important for scientific compute. It's also kind of the modern way of doing software development, containerizing everything. The bad of containers, and Docker in particular, are Docker containers need root access, which oftentimes means that admins are reluctant to have Docker support on HPC clusters. There's a performance penalty on non-Linux platforms, which could be bad for people who don't use Linux platforms as their base. We do, so we don't get that hit. But Dockers can be very hard to debug. It is a lot more complex to debug a distributed system, especially one that's been Dockerized in different containers. And we still have dependency issues in some respects. When you're specifying a Docker file and the requirements that are part of your project, you had to be very particular to take care of all of your dependencies, and oftentimes down to the level of specific version numbering inside your container. Docker Compose itself, which is a system to declare an entire environment of containers, can be complex as well. Of course, in our case, we've worked with a third-party cloud provider, the Massachusetts Open Cloud, to jumpstart our reach into cloud services. So there's a lot of good things about this, right? The Mass Open Cloud, or MOC, who has been very incentivized to provide cloud support to academic computing. They have deployed OpenStack and OpenShift. These are Red Hat technologies. And as we tried to get Chris to work with OpenStack and OpenShift, we had a lot of Red Hat support directly involved in the system, which really began to grow it out. And there's oftentimes powerful compute on cloud systems, like the Mass Open Cloud has a lot of PowerPC architectures. The provider, in this case, bad, is also growing. These are growing pains, particularly exacerbated when you're growing and your provider is growing. OpenStack and OpenShift themselves are subject to some kind of change. And sometimes there's custom code or tailored code that the provider might give to a project like ours, which can become invalidated when the provider themselves, and the ugly side, break things by doing updates. And we've had very many woes, even recently with authentication and single sign-on, when the provider updates some of their infrastructure behind the scenes. It all works for them. Our code no longer works. It's very hard to pinpoint the source of error because you're writing your cloud provider saying, hey, we no longer can log in. And they say, well, our systems are working perfectly. And you're saying, well, we didn't do anything differently. And this back and forth can be very difficult to manage and goes on for a long time before you get to the root of the problem. We've used Travis CI as our continuous integration platform. The good of Travis is that it's free. Any change to an open source repo triggers an event which results in a rebuild as well on Docker Hub of our containers, and then the testing of this automatically. So we can test in isolated fashion, autonomous or automatically, changes to parts of our system without disturbing our whole environment. The bad about this is that currently in our particular case, Travis only covers our development environment. And that's because our development environment uses Docker Swarm, while our deployment environment uses Red Hat OpenShift. And Travis is not able to provide an OpenShift environment. So we're not covering our deployment with our continuous integration, which leads to lots of issues down the line. The ugly about Travis is it can be very slow. The VMs that they use are very old. I think they are currently using Ubuntu 14 still as their VMs when they build your containers. And we can only test single service changes. If you think back to that picture I had of all the different parts of our system, sometimes by necessity, you're changing more than one thing at the same time. You're changing two things concurrently. in those scenarios, we're unable to have our test environment provide coverage for this, and we have to do it very much laboriously and locally to test these things. The core of a project, we've come to realize very strongly, is documentation. I would almost go so far as to say that a badly or poorly documented application is almost never used, because the documentation which tells the user how to use it either doesn't exist or is difficult to use. In our case, cognizant of this, we've tried very hard to have all of our repos and services have extensive documentation, with wiki pages, examples, tutorials, with a consistent formatting and style. In fact, the cookie cutter application that we provide developers, which they run, which builds a skeleton of their framework or of their application, also encourages them to write good documentation. The bad is almost the same as the good. We have too many documentation pages, and they're very hard to keep fresh. The more pages you have, the more things you need to keep track of. Because all of our different repos in this system have their own documentation, it becomes too distributed. And it's very confusing, we've discovered, for new users to really get a handle on where everything is. Out of sync documentation can be a death knell to your system. If you've made updates and your documentation doesn't reflect this, when a new user tries to run these things and it doesn't work, they lose interest very, very quickly. And it turns off developers as well. No matter how good something is, if it's badly documented, it really doesn't exist. And I almost can't stress that part enough. But one of the most important things of an open source project that we've discovered is its community. And it is very hard to grow community sometimes. In our case, what we've done is we've tried very hard to focus on developers and researchers to make it very easy for them to take their existing compute and with, we think, minimal amount of work, convert their existing program to something that will work in Chris. Of course, oftentimes people that join a project are attracted for different reasons. Oftentimes they're volunteers. And we discovered that volunteers working on our core assets of our system are very, very rare. Volunteer efforts are also very hard to focus. It's very hard as a, sort of on our side, on the inside of the system, to direct people and say, you must work on this, so it will be useful if you work here. Oftentimes we do that, but it's very hard to manage people, especially when their time is fractured. Hard problems take a long time for that dopamine reward hit. A volunteer is going to have to be very dedicated to want to spend 3 weeks working on your project before they get the benefit of a reward. So reducing that time lag is extremely important. We haven't figured it out yet. Of course, the ugly of people and community is there always are personality clashes. We've experienced this ourselves, and it's not unique to open source projects. In Linux, they have this benign dictator model, which sometimes seems to work well. That only works, of course, if everyone on your larger community respects the person in charge. Hopefully, in our case, this is the reality. When they don't respect the person in charge, then it leads to forking, which you probably don't want to have happen to your project. You end up spending a lot of time managing and a lot of less time coding or engaged in research, even if you are on the inside and trying to grow your community. And that's a very important thing that I think is oftentimes not fully realized. Growing community is quite hard, and it's oftentimes non-linear and discontinuous. Sometimes you have 10 people suddenly wanting to become part of your project. Other times, months go by and there's no new input. And even the people that join, there is sometimes of the 10, 20 people that might join for argument's sake, only 1 or 2 actually end up sticking around. But if you can make your project attractive, it greatly increases community. In our case, we've recently been working on a COVID-net plugin, which analyzes lung images, lung CT images with a neural network to make a prediction of COVID infection. And we found this very attractive. In fact, Red Hat has provided internal encouragement for their own developers to support open source projects like this. So we've had a huge influx of Red Hat folks wanting to help out, which is very difficult because all of the stuff I've mentioned before can lead to new developer overwhelming. We've realized we need a lot of support infrastructure for new people coming on board and a lot of direction and time. And again, with developers or volunteers in a project like this, the investment is never guaranteed to give a reward. People can drop out at a moment's notice, or they work very hard for a small amount of time, make a valuable contribution or begin to make a contribution, and they vanish. broken attention span results in loss of productivity and contribution. By that, I mean, we've discovered that people who want to contribute to a project, if they only have an hour or 2 or 3 a week, we have to be able to accommodate them to come to projects or part of our system that only need a small amount of time investment. Someone who wants to get into the innards of our backend, but is only going to spend an hour or 2 a week, will probably get frustrated and not become a useful contributor. Anyway, whirlwind kind of overview tour to wrap it up. I'm sure this is not a huge insight, but it's very true, and we've experienced that the computing projects are much more than just code. To grow, there's a huge need to focus on documentation, people, which together, of course, constitute communication. Communication, I think, is the real core of making an open source scientific project truly successful. And with that, thank you very much. And if there are any questions, I'm happy to entertain them. And I'm going to quickly stop sharing my screen. Oh, and I see there's a question from Simon. Thank you for your compliment, Simon. You greatly imagine reproducibility is a key aspect of this kind of work. Docker containers with really help. What else would you do, particularly on the data side, to ensure that results are verifiable and reproducible? Well, I would say that to a large extent, the use of some kind of container technology goes a very long way to having reproducibility and repeatability. Because these two terms, of course, are tied to a particular data set. On the data side, we don't focus so much on how do you somehow pin or specify what the data might look like. I'm not exactly sure if that's what you're asking. But I would be inclined to say that the focus on our end is very much on the compute. The reproducibility and repeatability is contingent upon, we guarantee you'll get that because of our container infrastructure, provided you give the same data all the time. As soon as you change the data, then it would become, then it's something else. All right.
If there are no more questions for Dr. Van der Westhuizen and Prof. Rudolph, we can break early. Thanks everyone for attending, and hope you enjoy the rest of the conference and the rest of your day. Thank you. Prof, can you please share the link for your presentation?
Oh, sure, hang on. Share screen, desktop 2. I can actually put it, let me put it in the chat. How do I do that? Type answer, all right.
There's one last question from Kasim.
Oh.
The only way we can collectively try to ensure that results are reproducive is if we make our findings and data freely accessible. Oh, that was the answer to the previous question.
Oh, yes, and that's very true. Certainly, if you're publishing a paper, our vision, of course, is that the data that you have in the paper, as well as all the compute that you did on that data, is freely accessible and available. And one of the reasons of this platform is to enable that as well.
We're still waiting for the link. Prof, I'm not sure if you shared it. Yes. I don't see it.
Do you see my share? Is there only, I could, I'm trying to put it in this chat thing, but it's not really working for me. Let me do it like this. All right, I put it in the answered section of the chat. All right, I can do that. I'll copy paste in the chat room too.
Oh. I copied it and pasted it to everyone.
Oh, no. Well done, thank you.
Well, I will wait. I don't know, Melanie, should we leave this chat open so people can just copy the link and leave whenever they're ready?
detection. And here, for example, what you're doing, you have this LIGO facility. The LIGO is the Advanced Laser Interferometer Gravimeter facility. And you have these colliding black holes that emit these gravitational waves. And normally the LIGO facility is able to detect these. And when you look down in this slide, so you see the actual signal that is recorded at both these facilities. And then when you look on the left to this very noisy signal, then you see the real signal that you must find in this very noisy signal. And this is actually possible by using neural networks. Neural networks are very, very tolerant against noise. So here, this is a very good use case to get, first of all, the simulation time much quicker and also the precision. Now let us look at an example here of computational chemistry. And in computational chemistry, we have here a software that's called Anachemy. And Anachemy is developed by the University of Florida. And basically it will compute from DFT data, so from high fidelity DFT data that is used for training, the energy surfaces of these quantum chemical simulations. And again, these normally with the classical algorithms to compute these would take a couple of minutes, and now this is down to a couple of seconds. So again, it is not running real time, but it makes a huge difference in the execution time for a researcher to be when they use this Anachemy. And then we have now two examples here from computational mechanics. And the first one here is the Volkswagen Data Lab with the deep virtuality. And here so here what they do is they directly overlay over this car body or motor structures. They overlay the vibrational noise. So this is done now in real time, and this of course enables the engineers to directly see visually what they get from the structure, and then they correct for the errors when they are seeing these things. Now let us look at another one that is this one here is very interesting because it shows you the Eulerian fluid simulation, and Eulerian fluid simulations are very precise. However, they are very, very time consuming to be computed. And one of the bottlenecks is, of course, the step number 8, that is the solution of the Poisson equation, and to find the pressure. Yeah. So you have to compute this pressure projection. Sorry. And so in order to do it, so the idea here that the scientists are implementing in this paper is then to train a network only for this step. And so you have the geometry, you have geometry, you have the velocity from the previous time step, and you have the pressure, and you compute the new pressure. And so this is done by training the network, and then they compare it as well with MantaFlow, and there is no loss in precision in the quality of the result. So this here is really impressive. Now let us look at Earth and Climate. So they do a lot. Obviously, they do a lot of research in this field. And here, for example, we have one that is to identify the tsunamis or hurricanes. And here, the idea is to have a succession of networks. So a first network that is trained from the satellite images. Yes or no, is there a hurricane in this picture or no? So it will just do a classification. If this classification says, yes, there's a hurricane in the picture, then it will do the localization. And it will find the longitude and latitude of the hurricane. And this is a very intelligent pre-processing. And you can also think perhaps to have these simple multi-stage networks running one after the other. And in order to pre-process your data, if you need only some, I don't know, some input data. So this is one possibility on how you can do this. Now let me come to yet another category of what you can do with neural networks. And so recently there was this idea of having the physics-informed neural networks. And this is one really to solve, for example, PDEs, so partial differential equations. And let us now look on how we can implement this. And so here on the left, we see the normal supervised data-driven approach. And here we train a network with the simulation data, and then we have some labeled output data. And this is how we train the network, by minimizing the error between the computed and the desired output. Now, when we want to have a surrogate, for example, for a PDE, then of course the network must first accept, of course, whatever is the input data. And secondly, it must also formally depend on the variables that we want to solve for. So for example, here we have a spatial and a temporal derivative. So in this case, the network must formally depend to these x and t, for example, and then we can compute the by automatic differentiation, we can compute the derivatives with respect to x and t. Here we see, for example, one implementation of this vortex-induced vibration problem of a flow past a circular cylinder. And this is the equation that is shown here with eta. And you will see that the density is multiplied with a second derivative. And then we have stiffness and the damping coefficient, do a damping coefficient with the other. And so here, of course, the input to the network is only a value at time t. So this is the only thing that we will have to show here. And then the network will have to compute the eta function. And we can also, or we will also put into the loss function all these physical losses that are shown here. So we will have the partial differential equation in the loss function. We will have the boundary conditions as well, and the initial conditions. So this is a little bit the idea here behind the physics-informed networks. So have it formally dependent on the parameter that you're solving for, and then having the boundary and the initial conditions also in your loss function directly to find a network that is a surrogate of the partial differential equation. And here we see a little bit more complicated setup, for example, for this heatsink. And the heatsink will, of course, simulate the airflow somehow that comes over it. So we must have all these turbulent CFD data. So first network is trained here with the Navier-Stokes equation. Then we will have a heat transfer in the fluid. So this is another network that we will train. And then finally, we also have a heat transfer in a solid. And then we train all these networks. And now we can run them to do the simulation and compare against the traditional solver who would have solved this one here. And here, for example, we see the heatsink with the airflow around and the gradient drops and so on. And what we see in a laminar flow or in turbulent flow, we get very close results or close results to commercial software or to open foam. And so we are never very far away. So this means that this method is very precise and can, of course, be used. The two different flavors that you see here with modified Fourier and sirens are special implementations of in SIMnet. So besides SIMnet, you can also use a lot of other software that is available here for NVIDIA. We have data analytics, we have all the HPC stack, we have artificial intelligence, we have hand-tuned containers that you can download from the NVIDIA GPU cloud. And of course, so we are good in visualization and gaming. And here I'm finished my presentation. Yeah, so here I finished my presentation. So if you have any questions, I'm happy to take them. Are there any questions, or I have here a Q&A open, and I think I have the chat also open. Anything that you would like to discuss? And no. Thanks, Deidre. Thanks, Washington. Yes. Okay, it seems like the chair has lost the connection, and so I think I'm finished. Yeah, I think I'm finished now, and so perhaps okay. So I will already end.
Okay, thank you, Gunter, for your presentation. Guys, I forgot to mention earlier, if there are any questions, you all are welcome to post the questions on the Q&A section. So after our next speaker, if you still have questions for Gunter, you can just put it up. But in the meantime, I'm going to introduce our next speaker. Our next speaker is Sven Brenner, and he's going to be speaking to us a bit more about the storage end of things as far as AI and machine learning go. Because as you guys know, there's usually a lot of storage involved with some of these applications, and you don't want that to be a bottleneck in your simulation. So Sven, over to you.
Thank you very much, Krishna, for the introduction, and thank you everyone for joining. Let me start sharing my screen. Okay, my name is Sven. I'm the field CTO of Accelero. At Accelero, we focus on software-defined NVMe storage, and in the past month and years, we have been working a lot with AI customers, and as Krishna already mentioned, very often storage turns out to become a problem for these customers, which they typically only notice too late. So this is kind of also the lessons learned and helping you to avoid these problems in the first place by being correctly prepared. So let's look at the overview. For this, we will focus on deep learning, which is a very storage intensive and very promising subdomain of machine learning. In the first part of the session, we'll try to characterize the problems for storage access with deep learning. Where do they come from? What do they mean for the storage systems? And then in the second part, we will, of course, talk about how to overcome these problems, make sure you're correctly prepared to avoid them. And then finally, we'll talk about what's next for deep learning storage, so what's upcoming. Let's start with a general, very brief description of what deep learning means. I assume many of you already know this, but to make sure that we're all on the same page. So deep learning is typically about teaching a computer to recognize certain objects that can be images or spoken language or other things as well. So let's assume in this example, we want to teach the computer to recognize animals. That's very easy to do for a human. You easily see that all these three images here are about dogs, but it's very difficult to program manually an algorithm that would actually recognize all kinds of dogs, right? So the way to overcome this is with deep learning. Deep learning means we show to the computer many, many images of dogs, and hopefully afterwards it will understand what characterizes a dog so that it can recognize new dogs that it hasn't even seen before. This showing the computer many examples of what we want to recognize is called the training phase, and the result of the training is called a model. And as you can see here, deep learning typically means that we go through various layers of detection. That's why it's called deep learning, because the detection is so deep through many layers, and each layer gets more complex. That's not super relevant for the storage part. Suffice to say that you really need many, typically millions of images to characterize all dogs in all kinds of shapes and sizes, because you can easily see for a computer to recognize this. Here on this image, we only see a single eye and a single ear. Here on this image, we have 2 eyes and 2 ears. So from the computer perspective, this is already very different. And here on the last one, we see only very few features of the dog, but for a human, it's still easy to recognize. For a computer, not so much. So to get to this high accuracy, right, a more practical example would be to recognize spoken language, where you want to make sure that the computer understands almost all of the words, not only 90% of the words, because then it's not very useful. Okay, let's look at the 3 high-level phases of deep learning. The first phase is what's called the data preparation. Here you just normalize the data, make sure, for instance, for images, they all use the same color palette, resolution, rotation, and so on. You focus on the relevant parts. of the images. That means you typically crawl the data once and maybe annotate it. It's not super storage intensive. You read it once, you write it once. Much more storage intensive is the training phase. This means you walk over all of the images again and again in different order, because all that impacts the way the computer learns. And when you're done with that, you do it again with a slightly different rotation of the images, or shifting the relevant object a bit and things like that. And then typically after doing this once, the data scientist is not happy yet with the results. So he will slightly tune the deep learning model and want to do it again and again until he's happy with the results. So this is super storage intensive, as you can see, because we have lots of small objects that we want to read again and again. The last phase is then called the inference, which just means you try if the computer actually detects what you want it to detect. Not as storage intensive as the training, so we will focus on the training phase here. The important thing, because this is an HPC conference, to understand for this is to which degree is this similar to HPC, and to which degree is it very different from HPC. Similar to HPC is that typically one host is not good enough, so you want to scale out, have a cluster of nodes, and this cluster is connected with a high-speed network. And the other thing is all work together on the same shared data set. So you want to have external shared storage that's available to all of the nodes. But where HPC is usually what I call strong scale out here, meaning the nodes typically are relatively small. You only have 1 or 2 CPUs in a node, and then you easily get to hundreds or thousands of compute nodes. And from the storage perspective, you focus mostly on streaming reads and writes, which works well with spinning disks. This is very different for AI typically. For AI, you start with the scale up, meaning you have typically 4 or 8 or maybe even 16 GPUs in a single computer. So the single computer is already a kind of supercomputer in a box, and then from there you scale out. We'll talk on the next slide about what that means for the storage. The other thing is that the workload here is primarily read intensive, because the training only reads all the data. And the other important thing is that we have lots of small and very highly concurrent random accesses to the storage, all these small images of docs. So what does it mean that we say the single host here is already a supercomputer in a box? From the storage perspective, it means that the I/O demands from a single compute node with GPUs are much higher than you would usually expect it for a single compute node. That's because we have fewer of them, right? Each one is more powerful and can process more data. So what you want to have from your storage system is high single client performance. The other thing is it's very read intensive. So the classic concept for HPC that was modern for a while, called burst buffers, won't work well here, because burst buffers are primarily to add flash to a system and cache the incoming writes. But here it's not about writes for AI, it's about reads. So the burst buffers don't really help here. And the third important thing is that we have lots of small and highly concurrent accesses to the shared storage. That means spinning disks are about to fail for this by design, because they hate small and highly concurrent accesses. It makes them seek a lot and makes them really slow. Which brings us to the conclusion that NVMe drives are the de facto standard for deep learning storage today, just because they really embrace, other than spinning disks, this high concurrency and small random accesses. They are only chips, they don't need to seek. So they embrace it, and they actually only get really fast when you access them highly concurrently. While it's easy to add an NVMe drive to any host these days, the real challenge for the storage industry has become to make this performance of the NVMe drives available over the network as shared storage, because that's not so trivial if you're coming from software-defined storage that has been designed for spinning disks and for very different latencies and IOPS expectations. You're already in this session, so you're about to learn what this problem is, or already learned it. But what I saw very often is that this problem of storage is often recognized only too late. So where does that come from? Well, that's simple. Typically, when you're starting to evaluate deep learning, you start with a very small system, a rather small data set. So what you typically do is you take your one or few GPU nodes, put the data set on internal local NVMe storage inside the nodes, and everything runs fine. But then when you want to do some serious deep learning, you start to need the scale out and the shared external storage. And then that's when you recognize that the classic storage system is not really suitable for these high IOPS demands that come with deep learning training. And that's when you typically only start to notice the problem. So it's important to understand the problem upfront and then just be prepared for the new kind of access patterns that you will have here. So just to summarize, what are these typical deep learning storage requirements, right? When you're a data scientist, so that you can tell your system administrator to make sure the solution meets these demands. What you need are very high read IOPS for lots of small random accesses, right? All these small doc images, for instance. And very often, you even want to work with lots of small files to avoid the extra overhead of converting all the small files into a few larger files. That's even more convenient for you and will save you a lot of effort and time if the storage system can efficiently work with lots of small files. And then in the end, but that's very often a given already, you will want to have the ability to scale to higher performance and higher capacity whenever needed, just because when you learn how great deep learning can be and how amazing the possibilities are, then you will, of course, want to do even more with it. But how much performance do you now actually need from your storage system? Trying to quantify this is not so easy because, of course, it highly depends on the objects that you're training on and how your actual model works. But just to give an example, very often storage vendors run benchmarks with the combination of ImageNet, which is an annotated image database available on the internet, TensorFlow, which is a deep learning framework, and ResNet-50, which is the neural network for the training. Unfortunately, this combination has very limited practical relevance from my experience, at least, because it gets very easily bound by the processing speed of the GPUs. What I see in the real world is that the applications are typically much more optimized than this combination here. And so the storage demands are typically much higher. Some of our customers, for instance, are working with hundreds of millions of only 10 kilobyte files. So to get to good performance for that, right, you need a much stronger storage system than for this case. So what does this case mean? For the combination of ImageNet, TensorFlow, and ResNet-50, NVIDIA specifies that the maximum that the GPUs can handle are about 17,000 images per second on a DGX A100 system. So that means at this point, it would not make a difference if your storage system is any faster than that or not. And what does that mean for the storage system? ImageNet has an average file size of about 100 kilobytes. This particular test first converts all the lots of small image files into a few larger files, so-called TensorFlow records, which already changes the storage access pattern, but also means that you have an extra wait time for this conversion always upfront. And then in the end, from the storage system perspective, 17,000 images per second with 100 kilobyte size means you will read at about 1.7 gigabytes per second. and do random accesses to these 100 kilobyte files. If your storage system would be based on spinning disks and you want to reach this performance level, then a single spinning disk can do about 100 random reads per second for this access pattern. So you would already need 170 spinning disks to satisfy the performance here and keep the GPUs from stalling on I/O. So that's already quite a lot for just a single DGX A100 system. On the other hand, a single NVMe drive, depending on the generation of the NVMe drive, PCI generation 3 or 4, which is much faster, the single NVMe drive can already deliver 3 to 7 gigabytes per second, so can already deliver more than the DGX A100 can consume in this test, just to show the difference between the two. And then the other factor is that ImageNet is only 150 gigabytes in size. So after reading it once into the large memory of a DGX, the next round would already be served completely from cache. So it's no longer a realistic case, because a realistic training would use a much bigger database. Which brings us to the next question of what better test for storage systems do we have available to characterize them? And I searched for that, and there does not seem to be any industry-wide accepted benchmarks for these cases, but we needed, of course, to be independent of the processing speed of the GPUs for a particular benchmark, just to find out how quickly your current system, for instance, can handle these small random accesses, so that you know if it will be good enough or if you need a better system. And when you have that better test system, if it will really meet your demands. And on the other hand, as a data scientist, of course, it's also important for you to find out how fast the storage system can ideally be, so that you know if when you change your access pattern, if you will be bound by the storage system or not. So to help optimizing your application. So with no such benchmark available, I went ahead and just created a new benchmark for storage systems, which I called LBencho. LBencho can work with random access in lots of small files, or can also measure random access in few large files, so that you have both cases covered. It can also run distributed across multiple compute nodes, and it can even work with GPUs. So you can really measure which performance from the storage system you can get through to the GPUs. It's available for free. Here's the link to GitHub. So let's look at a few examples of how this works. Just recently, I had the opportunity to test a DGX A100 system at the University of Pisa. The storage system connected to this was one quad server chassis with 16 NVMe drives and connected via 4 times HDR InfiniBand to the single DGX A100 system. For the software-defined storage, to make the NVMe drives available to the DGX A100, we used the BGFS parallel file system together with Accelero's NVMesh, which provides the software-defined RAID for high availability across the NVMe drives. And here we have some performance examples that came out of this rather small entry-level system, I would call it. Reading in this example 1 megabyte, so that's a rather easy case, you could say, for storage system, because it's relatively large reads, but to see which kind of streaming throughput we can get. We did some direct reads here, which means we're bypassing the cache to make sure that all the data is really being served from the NVMe drives directly. Nothing is coming from the cache. We're doing random reads in these large files with 128 threads. And the throughput that we get here is about 50 gigabytes per second at 5% CPU utilization. That's for reading these large chunks into the host memory. The next interesting question is, of course, will it be the same when you actually want to forward the data into the GPU memory? Because that's where you actually need the data in the end. So El Bencho also supports that. You just provided the CUDA IDs of the GPUs. There are 8 GPUs in total in a DGX A100. So we have the 8 IDs here. And what you can see is that there is a bit of a difference between the two results. Here we're only reading at 50 gigabytes per second into host memory. When we also transfer the data into GPU memory afterwards, we're down to 45.7 gigabytes per second at about 7% CPU utilization. So I would say these numbers are quite good, but you of course need to verify with your storage system at hand whether the difference is about the same or maybe much bigger than in this case. To have something that comes closer to the ImageNet case, I also ran a test with only small files, 128 kilobyte file size in this case. First test was again reading them only into host memory. And what came out are about 140,000 files per second that can be read into host memory at about 6% CPU utilization. Why is the CPU utilization relevant? Because typically your application will want to do some extra pre-processing of the images before they are transferred into GPU memory. So lower CPU utilization is good for this case. And then the next test is again, what performance do we get when we, after reading into host memory, transfer all the files also into GPU memory? Then we can still read at almost 140,000 files per second. CPU utilization slightly increases, but the rate is almost the same. And as you can see, this is of course a much higher result that we can read here from a single client than we would need for the ImageNet and ResNet 50 test. But from my experience, it's also a very important result because this rate comes closer to what customers actually expect from their real world applications. Okay, which already brings us to the last slide. What's next for deep learning storage? Because of course, NVIDIA very often only talks about the compute part. That's normal. Intel and AMD for their CPUs also mostly focus on the CPU part, not on the storage part, but at least recently NVIDIA became more aware of storage being a general problem for deep learning. So they are working on a new concept, which is called GPU direct storage. What does GPU direct storage mean? In the examples that I showed you before, how do the reads work? They come in through the network, get transferred into the main memory of the compute nodes, and afterwards transferred from there over to GPU memory. So for certain access patterns and certain file systems, this extra hop here through main memory can become a bottleneck. And GPU direct storage is based on a new concept where the data can flow directly from the network card into the GPU memory, so that you don't need to put it into main memory first. From the application perspective, that's a very simple change. Instead of your normal read function, you have a new QFile read function, which has very similar parameters. The only difference being that the buffer that you give to this function is not a buffer in main memory, it's directly a buffer in GPU memory. So it requires a relatively small and easy change from the application perspective. The changes are a bit more complicated from the storage system perspective. So many vendors are still working on adding GPU direct storage support, and it's still currently only in beta phase, but already in public beta phase. So you can already download it from the NVIDIA website if you want to try it out. As you can see from the from the results that we saw before for this particular combination of BGFS and NVMesh, I think the numbers are already pretty optimal, so they would not be much different with GPU Direct. But I think it's great that NVIDIA is at least now raising the awareness for GPU storage so that we can help prevent people from running into these issues only too late. And with that, we're at the end of my slides. So I thank you for attending, and of course look forward to you doing great things with AI in the future. And I will of course be happy to answer any questions if there are. And otherwise, after the session, you still have my email address here, so feel free to contact me anytime, of course.
Okay, thank you, Sven, for the good presentation. I am waiting on any questions that people might have. I don't see any at the moment. I will give you guys like another 2 minutes so you can post some questions too. Okay, so there is one in the chat, which was IOR something that you could not configure to work for this? I'm guessing that's for the memory thing. As a widely trusted benchmark, a configuration for it might be easier for people to trust.
Yes, of course, as part of Elbencho development, I always compare the results to IOR. So if you run the same access pattern with IOR, you should get the same results. IOR is mostly focused on a few big files. You can do the random access, but IOR would not work well with small files. So there are other benchmarks that focus more on lots of small files, like MD test, for instance, right? And our customers typically had problems accepting that they need many different benchmarks, FIO, for instance, for the block devices. So typically 3 different benchmarks just to benchmark a single storage system. And many of them also had problems with MPI, because if you're not familiar with MPI, then it's hard to understand how to use that. Although the general concept is simple, of course, once you understand it. But that all led me to the assumption that it should be easily possible to have just a single tool that can run on block devices and work with large files and also with lots of small files. So that's how I created Elbencho. And the other thing is, of course, that IOR does not support GPUs. While for Elbencho, of course, I added right from the start also support for GPUs so that you compare with that. And it also already has support for GPU direct storage. So in case you try that out, Elbencho will also allow you to do that.
Okay, thank you for that. And then there's one more from Dr. HPC Tole. So thank you, Sven, for a good presentation. Is BGFS ready for GPU Direct?
Yeah, I can't speak directly for the BGFS team. As far as I know, they are working on adding GPU direct storage, but I can't say when it will be available. It's not available yet in the current public version. So I would suggest to talk to ThinkPark, the company behind BGFS, directly and find out more about that.
Okay, so I think that's all the questions that I've seen. So that is all. Then thank you, Sven, and also thanks, Gunther, for your presentations. And this brings us to the close of the session.
Okay, thank you and bye, everyone.